Okay, guys, let's just continue in our tutorial. So this is the second tutorial, and it is a physics tutorial, and I thought it is very important that before we can begin with this tutorial, we need to have all the formulas that would be required in place. We are not going to deal with the simple things. Nothing is simple in physics. Physics requires that you think and you make sense and logic of your thinking, and there has to be mathematical models that you use and mathematical formulas in order to substantiate that which you think it's a possibility in your perception. So I have gathered all the formulas in here, and I believe we will need some or most, or if not all, of these formulas in order to explain that which needs to be explained. And then I think I have a problem in here that I have placed. We will deal first with that problem. That is fine, but I don't think it belongs in here, because here we were just looking at the formulas that needs to be used. So I think I might have made a mistake of just placing this in here, but it's fine. We will deal with that. So the first formula that we have, the index of refraction is the speed of light in a vacuum divided by the speed of light in a medium where light is traveling inside of. Light doesn't require a medium in order to travel. This is very important. The formula does not imply that light requires a medium in order to travel. This was made clear by Albert Einstein in relativity, which is quantum mechanics. But we will deal with quantum mechanics when time is right. For now, we are looking at the classical view of light. So the speed of light in a vacuum, because in classical mechanics, a light requires a medium in order to travel. This is the classical view of light. But in quantum perception, in the way in which we look at light in quantum physics, light doesn't require a medium in order to travel. This is very, very important. But somebody can argue and say, is air not a medium in itself that light is traveling through? Let's just leave it at that. Now we are saying the angle of refraction is the speed of light in a vacuum. I think we will see that the value of the speed of light in a vacuum divided by the speed of light in a medium where light is traveling inside of. We will need this formula, I believe, as we proceed. And the index of refraction is equal to the wavelength of light in a vacuum divided by the wavelength of light inside of a vacuum where light is traveling on. Very, very important that we understand all that. Right. I think there's a problem in here. Hence I'm saying, let me just get rid of this. Very good. Let's go back. Right, and therefore we are saying this is a Snell's law. The index of refraction n1 sine theta 1, the index of refraction in the first medium is equals to the index of refraction in the second medium, and then this is the angle that we form when we are in the first medium, and this is the angle that we form when we are inside of the second medium, the sine of that angle. Very, very important. So we are here speaking about two different mediums. So for two different mediums, the index of refraction would be different, and we are taking the sign of the angle that light makes inside of that medium. The index of refraction in the second medium, remember we are referring to two different mediums, multiplied by the sign of the angle that it makes inside of the second medium. So this is what we refer to as the Snell's law. Be that as it may, we have, let me just go back. We are therefore saying the wavelength in the first medium divided by the wavelength in the second medium. This is equals to the speed of light inside of that first medium divided by the speed of light inside of that second medium. And this is also equals to the speed of light divided by the index of refraction in the first medium, the speed of light divided by the index of refraction in the second medium. And remember here, we are not saying C0 or C1 because this is just the speed at which light is moving. And then this is equals to the index of refraction in the second medium divided by the speed of light in the first medium. It is very, very important that we understand that. And then here we are saying W is equals to twice B plus A, and then when you make B the subject of the formula, this is what you get. We will see what this really means when we get into the problems. Maybe that would require this, and if there are problems that doesn't require that, you will just have to wait for another day. And then we come just here and we learned from the previous tutorial that the incident ray is bent when it comes across the line of the normal that makes an angle of 90 degrees. And we see that when light moves inside of a medium that allows light to penetrate, we know that the angle of the index will be greater than the index of the refracted ray, because you know that when light moves from the first medium to the second medium, light is refracted, and as a result it bends away from the normal. And please note that this is n equals 1, and we know that when n equals 1 and this angle is bigger than that angle, that simply tells us the speed of light here is higher, therefore makes a greater angle. The speed of light is slower, therefore making a smaller angle. And when it enters inside of a second medium, light is bent away from the normal, and as a result of that we have n1, n2, and then it comes out of glass, for example, and then we have n3, and we can calculate that which is required in there. One possibility we can do there. Okay, and then here we just showing that when you have the index of refraction n1, and you can see that the wavelength here it's bigger because light is moving at a higher speed, and here you can see that the wavelength is smaller as a result that light is moving at a smaller speed, the index of refraction there. And we know that n2, they say, is bigger than n1. So the index of refraction here is bigger because the wavelength is smaller, and the index of refraction here is smaller because the wavelength is bigger. So there is an inverse proportional relationship between the index of refraction and the wavelength. We can see the bigger the wavelength, the smaller the index of refraction, and the smaller the wavelength, the bigger the index of refraction. So the wavelength 2 is smaller than the wavelength 1. That would tell us that the index of refraction here is bigger, C divided by V. Please do not forget that. The index of refraction is equals to C divided by V. And yeah, here we have it. And C is the speed of light in a vacuum, and V is the speed of light in a medium. Very, very important that we note that. All right. And then the professori continues in this in table 22.1, and we are looking at the indices of refraction for the various substances that one has, and they are measured with light of a vacuum wavelength. Wave naught equals 589 nanometers. It is very important that we note this, that the indices of reflection for a various substances, they are measured with light of a vacuum wavelength, and that wave naught is 589 nanometers. So please, it is very important that we note that this is nanometer. And then we have the substances, and then we have them, and these are their index of refraction. And what can we tell about these index of refractions? We know that let me just do this. Okay, we know that if the index of refraction is bigger, therefore we know that the wavelength is smaller, and if the index of refraction is smaller, therefore we know that the wavelength is bigger. So looking at this, there are many things that we can say. We can see that the index of refraction here is bigger, therefore the wavelength is smaller. And we can see for this one, for example, that one, this one is smaller when compared to the others, therefore the wavelength is bigger. These are some of the things that we can look at. Very, very important. And then we can come here, gases at 0 degrees Celsius, 1 atmosphere, and air. Look at the index of refraction. The index of refraction is smaller, therefore the wavelength is bigger, and also carbon dioxide. So it looks like when the material through which light is traveling on, when that material is a gas, because this is air, and air in this state, yes, they are the gases, but at 0 degrees Celsius, 1 atmosphere. Therefore, when the index of refraction is smaller, the wavelength is bigger, and so on. All right, so this is just me trying to explain that which needs to be explained. Right, we can continue in this, and then we are having a problem now. We are now having a problem. And what is the problem, Papa Fanzu? They say to us now, a light ray of wavelength 589 nanometer produced by a sodium lamp traveling through air is incident on a smooth flat slab of crown glasses at an angle of theta 1 of 30 degrees to the normal as sketched in figure 22.1. Jesus, I've made some mistakes in here. I think this is what they are referring to. Let me just cut this, and let me just try to paste that in here. I think this is what they are referring to. I think they are referring to that. Right. Let me try to move this one a little bit. Papa Fanzo, let me just do that. Right. Suppose this is what we have now. We can continue with our work. So this is what we have. A light ray of wavelength 589 nanometer produced by a sodium lamp traveling through air is incident on a smooth flat slab of crown glass at an angle of theta 1, which is 30 degrees. So we are provided with an angle theta 1, which is 30 degrees to the normal. There it is, as sketched in figure 22.11. Find the angle of refraction, which is theta 2. That's the first question. B, at what angle theta 3 does the ray leave the glass as it re-enters the air? And then C, how does the answer for theta 3 change if the ray enters water below the slab instead of the air? So this is one of the questions that we need to answer. Right, how am I going to do this? I think I will go in here because I want us to have a step-by-step solution for that we may understand exactly what we are talking about. Therefore, it is very, very important that we have an interactive learning in all this. All right, let's just wait for it to load up so that we can begin working on that. Now here it is, here we are, and we will try very much to work on that. Now I'm going to mention things a little bit slowly that we may have an insight as to what needs to transpire here. So they are looking for theta 1, and we are provided with the wavelength of this incident ray, and we know that the wavelength, do I have any symbology that I can use for the wavelength in there? Oh, sorry. Let me check if there's anything there that one can use. Yes, there it is. So we have the wavelength of the incident ray, that is equals to 589 nanometer. This is what we are provided with. And then secondly, what is it that is provided to us? I think it is very important that we note these things very, very well. So that one is provided for us. And then secondly, what is it that is provided to us? Right. Traveling through air is incident on a smooth flat. Okay, that is that. To the normal, find the angle of refraction theta 2. All right, so one thing that we need to note here, I need to know the index of refraction. I know that the index of refraction inside of a vacuum. So let me just take you back here, because I want to use the Snell's law. I can find N1 for this. Let me show you for air, and I am provided with the angle for the air, which is 30. I can find N2 for glass, and then I can be able to find angle 2. So I need to go to a table, and from the table I need to find the index of refraction for a glass. So let us just look around and see what we can get. Diamond and so on, glass, and this is the flint. Now the question is, should we use that one or should we not? Should we use that one or should we not? Is this the only one that is provided? Let me go and check once again. Carbon tetrachloride, we have water, and we have glass flint. So this is 1.66. Can't I find maybe a different value for that? Fused quartz, okay, and then I have a glass crown. So between glass flint and glass crown, which one should I use? Now let me go back to the problem. A light ray of this wavelength produced by sodium lamp traveling through air is incident on a smooth, flat slab of crown glass. So it is a crown glass that they are speaking about. So I'm going to take the index of refraction as 1.52. As what now? As N2. So this is my N2, but let me just wait. I don't want to find N2 first. What I want to find is the index of refraction for air, and they are saying to us, very important, that we should go back to this. A light ray of wavelength, this produced by a sodium lamp traveling through air. So let's go and check. Air, I know that the index of refraction is almost 1.0. So I'm going to take that value exactly as it is. So I'm going to say n1 for a. In fact, let me do this. Let me use a subscript n1 for a, and I'm going to say this is going to be 1.000293. Right, so I have the wavelength. Remember the formula that I want to use. I want to apply Snell's law, and it just talks about n1 sine theta 1 and n2 sine theta 2, and it has nothing to do with this wavelength. It has nothing to do with that. So okay, that is fine. So I have an angle sine theta 1 is equals to 30 degrees. It was provided in the statement there. Theta 1 is 30 degrees. So now I'm fine. I have n1 and sine theta 1. Now I need to find n2. So what is the value of n2? So my n2, they said is traveling through air and then flat slab of crown glass. So flat crown glass, it's 1.52. So I have n2, which is 1.52. Very good. Now I need to find the angle, because that's all what is now needed. So let me go and apply the Snell's law. And I know that Snell's law, n1 sine theta 1 equals n2 sine theta 2. So this is exactly what I'm going to do. So I'm going to say n1 sine theta 1 back theta 1 is equals to n2 sine theta 2. So I can just copy this, sketch, and paste it there, and we can use 2 there, and I can use 2 there. Right. So now remember, I'm looking for theta 2, and what is that going to be? I'm not going to manipulate this. I'm just going to go to my calculator, fx, this, and I'm gonna demonstrate this in here. So I have the division there. Let me take n1, which is 1.123293, and I'm going to multiply this by sine theta 1. So the sine of 30, and I am going to divide all this by sine theta 2, which is sorry, not by sine theta 2. Remember, I'm looking for that angle, by n2, which is 1.52. And what value will I find? I find 0.32. What is that now? That is the value of the angle. So theta 2, in fact, sine theta 2, because remember I was looking for sine theta 2, I divided by n2, which is 1.52. So sine of theta 2, so let me just copy this and paste it. So this is equals to the value that I have there, 0.329043. We don't round off, we only round off when we arrive at the final answer, 75. So in order to find theta, you you divide both sides, so you will say theta 2 is equals to sine the inverse, because remember the exponent of sine here it's positive. So remember, you divide by sine. When this goes on the numerator, it becomes negative. This is basic arithmetic. So we will say sine the inverse of all this. Copy this and paste that, and then we can find the value of theta 2. So just copy this and just paste that, and this is equal. So I'm going to come here and I'm going to say shift sine the inverse of 0.32904375, and we find that as 19 point this. So this would become the answer for us for this angle, this theta 2. Now I want us to note something. Look at this angle, it's at 19.2, and the first angle when light entered inside of this second medium, the angle was 30. So the angle has decreased from 30 to 19. What does that tells us? That firstly tells us that we know that the bigger the angle, the bigger the wavelength. So the wavelength is bigger here, the wavelength will be smaller there. And secondly, what we can see that is that the angle is bigger, okay, and the angle is smaller there. Therefore the wavelength is bigger here and the wavelength is smaller there. Those are the two things that we need to note. And then secondly, because this angle is bigger than that angle, it tells us the speed of light here is much faster than in there. And then secondly, because the index of refraction here is smaller and there it's bigger. What does that tells us about the wavelength? The smaller the index of refraction, the bigger the wavelength. Very important. And then where do we see that? Let me just take you through a few things. Let me take you here. The bigger the wavelength, as we can see there, and N2 is bigger than N1. So when N2 is bigger than N1, the index of refraction, when the index of refraction in here is bigger than the index of refraction in here, that tells us that the wavelength is smaller in here and the wavelength is bigger in there. And then that ultimately tells us that the speed of light is bigger in here and the speed of light is smaller in there, which ultimately tells us that the angle here is bigger than the angle there. The speed of light is greater and smaller in there. These are some of the most important things, highly important stuff that is worthy of noting. Very important. So by just looking in here, and seeing that the index of refraction of air is greater than the index of, is smaller than the index of refraction in crown, that simply tells us that the light here is faster than in there. This is very important, and the wavelength there, it's much bigger than the wavelength there. And then how do we see that? We can see that in here. If N1, if the wavelength in 2 is smaller than the wavelength in 1, that should ultimately tells us that the speed is much higher in there. These are the things that are worthy of noting. So we have found the angle of refraction, which was a theta 2. And then they continue for number B. At what angle theta 3 does the ray leave the glass as it re-enters the air? So light has traveled. Okay, let me just do this very quickly. Let me just have something to eat and we will continue in this. Right, we can continue in this, wonderful people. We can continue in this. Right, we found theta 2. That was a little bit simpler for us to find the angle. All right, let us just find that angle very quickly. That is 19.21. So the value is 19.21. Remember, it's an angle, and therefore it is in degrees. Very, oh sorry, raised to an exponent of the degree. So this is the angle in degrees. Please note that we are dealing with angles in degrees and not in radians. Okay, that's not all what was required. Find the angle of refraction theta 2, and then number B, they say at what angle theta 3 does the ray leave the glass as it re-enters the air. So already we have the angle of refraction for the glass, and then we know the angle of refraction for the air, and we can just simply use that. So we are going to use the very same angle. Right, so we are going to say n1 sine theta 1 equals n2 sine theta 2, and this will be the angle of refraction for the glass. We already know n, and the value of n1 is equals to what? Let us just quickly go and see there. Let me just quickly come here. It was a class ground that was 1.52. So I have 1.52. I will multiply by the angle that I have just found in there, which is what was the value? Let me just check. 19.21. So I will come here and say the sine of 19.21, and I am going to divide that now. Remember what the question is saying. The question is saying that at what angle? So I'm looking for theta 3. So I am going to divide that by n2, which is 1 theta 2, n1, which is it was provided for us as 1.000293. So let me just say 1.000293. That is the index of refraction for the air, and I will find that value as 0. Let me just see very quickly. The value would be 0.4999. That would be the value, and if I take sine the inverse of that, remember I said 1.52 divided by the angle of refraction for the air. Let's just check. Remember that is theta 3. At what angle theta 3 does the ray leave the glass as it re-enters the air? So it is leaving this angle, n2 theta 2, which is this. Let's just, oh sorry, so we are in here, n2, which is 1.52 multiplied by the sine of that angle, which I have found as 19.21, 19.21, oh sorry, and I have to divide that. Now let us check this. n1 sine theta 1 equals n2 sine theta 2, so I'm going to divide that by n2, which in this case is air, and I know the value for air would be the value of 1.000293. 293, and I find this as the value, and I'm going to say 0.4999. So let me just say sine the inverse 0.4999, and I find that value to be 29.99, and this tells me the angle there it's 30. And is that correct? This is the very first thing that we need to ask ourselves. Is that correct, that we could be able to find that as like that? And yes, this is true. This is very much true, because remember, let me take you back here. It entered with an angle of 30. When it entered inside of a second medium, the angle was 19.21, and then when it goes back to the air, the angle has to be the same. So we find that the angle is 30 degrees. So that would be the value of theta 3. At what angle does the ray leaves the glass as it re-enters the air? And then we can proceed to number C. How does the angle for theta 3 change if the ray enters the water below the slab instead of the air? And we can calculate that. How does the answer for theta 3 changes if the ray enters the water below the slab instead of the air? So one most important thing that I think it's worthy of us noting there is that we need to find the index of refraction for water. We need to find the index of refraction for water, and the value there is 1.333. So we need to find what there? We need to find how does the angle for theta 3 changes. So let's go and find that angle, and we are going to rely very much on Snell's law. All right, let's come here. Now, one most important thing, N1, which would be the value in here, which we found as 1 point. Remember, it moves from the glass to water now instead of the air. So the angle, the index of refraction for glass is 1.000293, and we multiply by the angle there, which we found as 19.2. 19.2, and I'm going to divide this by the angle of by the index of refraction of water, which is 1.333, as we saw it in here. 1.333. H2O at 0 degrees Celsius. This is all what we have, so we are going to use that. And then we will find, there's a bracket there. Let me just quickly get rid of that. And we will find that as the value there will be 14. What is this now? This is the value of a sine. We find that very, very important. We find that sine theta is this. This is very, very important. We have the index of refraction for glass multiplied by the angle that was there. Let me see whether this was correct. 1.000293. Yes, this is correct. I multiply that by the angle that I found there. The angle there, which is 19.2. So you see what I've did there? I substituted the angle, not the sine. So please, let's be careful of that. We need to use the sine of that angle there. Please, let's be careful. The sine of 19.2, not necessarily the angle itself. No, the sine of that angle. Very important. And then when we press the equal sign, this is what we get. We get the value there as being equals to that. And now I'm looking for the angle now. Theta 3, the angle. Instead of moving from the glass to the air, we wanted to move from the glass to the water. So I'm going to have sine the inverse of 0.246. Sine the inverse of 0.246. And I find the angle to be that. Now, is this true? Is this true? This is the question that we need to ask ourselves. Is this true? That this should be in this way. Right, let us go and verify that. Now we are here. Let me just take this out. And now let's look into this. We have the glass and the index of refraction is given to us as 1.000293, and we multiply that by the sine of an angle that we have found, which is 19.2, and this is equals to N2, which is the index of refraction of water, and that is equals to 1.333. Let's do that. 1.333. I multiply that by the sine of theta, which is what I'm looking for. Sorry. Right, I know how to do that in a calculator. Let me just say fx very quickly. And I know how to do that. And I know from there I will have this 1.000293, the sine of 19.20, and I'm going to divide that by 1.333, and I will find the value as that. This is exactly what I will find. So this is sine of theta 3. Very, very important. The sine of theta 3 is that. Very, very important. So what did I do there? Why did I use 1.000293? Why did I use that? Why did I use this? Is this in the first place correct to use? No, it is not correct to use because it is no longer moving. Let me show you. It is no longer moving from air. It is moving inside of glass to water. So I cannot use the index of refraction of air there. I need to go and use the index of refraction of glass, the glass crown, which is 1.52 there. So here we will need to use, we need to make these mistakes so that you see exactly what is happening. We are not here just as a genius that makes a tutorial and everything just goes on well without any mistakes. You will never learn a thing in that way. We need to allow ourselves mistakes so that we understand exactly why things should be the way in which they are. So here we are in glass. We take the index of refraction of glass, multiply by the angle there, and the angle should just tell you that the 19.20 was the angle that we found when light was moving from air to the glass. So how can we use the index of refraction of air when the angle there was 30 and not 19.20? Very important that we take note of these things worthy of noting. Papa sketch worthy of noting. And right, and then when we calculate there, we find this as the value now, the correct value now, 0.375. And then I can just say sine the inverse of 0.375. And then we find our answer as 22.02 degrees. So this would be the angle if light was to move from glass and not to the air but inside of water. It would create an angle of what? It will create an angle of 22. So what does that tells you in contrast to the previous answer of 19 of 30? It tells you that light will travel even slower when it moves from the glass to the water. But one thing that I want you to note that the angle has increased when compared to the angle inside of the glass. It was 19.2. Here we get a value of 22 when it goes from glass to the water. What does that tells us? It tells that the wavelength inside of water is bigger. And it also tells us that light travels faster inside of water than it does inside of glass. This is one thing worthy of noting. It is more than worthy that we note that. Now let's have some reading here. Let's just have some reading that I think it is very important for us to look into that. So let us look at the remarks. Notice that the light ray bends towards the normal when it enters a material of higher index of refraction. We know that the index of refraction is bigger here, and the index of refraction is slower there, therefore light travels much faster and the angle is much bigger. We saw that. And away from the normal when it enters a material of a lower index of refraction. This is very, very important that we notice that light rays bend towards the normal when it enters a material of higher index of refraction, and away from the normal when it enters a material with a lower index of refraction. Very, very important. In passing through a slab of material with parallel surfaces, for example, from air to glass and back to air, the final direction of the ray is parallel to the direction of the incident ray. The only effect in that case is the lateral displacement of the light ray. I think when we look at quantum mechanics, we will go deeper into that. Right, let us look at question 2.22.2. If the glass is replaced by a transparent material with a smaller index of refraction, will the refraction angle theta 2 be smaller, larger, or unchanged? Let us just think about this. It is very, very important that we think about that. They say, if the glass is replaced by a transparent material that allows light to be reflected with a smaller index of refraction. If the index of refraction is smaller, therefore the speed of light is bigger, therefore is the angle, therefore is the wavelength. Will the refraction angle theta 2 be smaller, larger, or unchanged when we compare to glass? Will the refraction angle theta 2 be smaller, larger, or unchanged? It has to be larger. It has to be larger if glass is replaced by a transparent material with a smaller index of refraction. And then why do we say that? Let us go back. Let us go back. Okay, let me do this. Now, we saw that when light is traveling in air, the index of refraction is smaller. And how did we see that? We saw that in here. The smaller the index of refraction, the bigger the angle and the faster the speed of light. Right. If the glass is replaced by a transparent material with a smaller index of refraction, will the refraction angle will the refraction angle, and n equals c over v, will the refraction angle be smaller, larger, or unchanged? It will be larger. Why? Because light will be traveling much faster inside there. The wavelength will be bigger. And the faster the light traveling, the bigger the wavelength, and therefore the smaller the angle of refraction. Right. Let's go to exercise 22.2. Suppose light ray in air n equals 1.0 enters a cube of material n equals 2.50 at 45 degrees. Right. Angle with respect to the normal and then exits the bottom of the cube into water. At what angle? At what angle to the normal does the ray leave the slab? And they give the answer as 32.0 there. We are going to try and solve that. Sketcher will try very much to solve that. Now let us look into this. It is very, very important that first of all we write down the data that is necessary. Please let me not get rid of the Snell's law. What will I be without the Snell's law? I'm not going to get rid of that. Right. And I'm not going to get rid of this. I'm just going to change the values in there. Right. Let us continue in this. Let's continue in this. Right. Let's have a reading once again. They say to us now. Let me just place this in here. Suppose light ray in air n equals 1. So I'm going to have the index of refraction in air as 1.00, just as it is provided for me there. Camtasia has a tendency of net recording, guys. It is very important that I place this closer where I can see. Proceed, Mlochwa. Proceed, Sketcheket. Right. We have that the index of refraction for air is 1.00, that is C divided by V, enters a cube, therefore I have N2, that is equals to 2.50, that is fine. At an angle, remember, it enters a cube at this angle. So sine theta 1 is 45.0 degrees. Can I just do this? Can I just do this and just use the degree measure there? Can I just do this? Degrees, okay, that is fine. Angle with respect to the normal and then exits the bottom of the cube into water n equals this. At what angle to the normal does the ray leave the slab? Right. Remember they said okay, and then exits the bottom of the cube into the water. That's fine. And then they are saying into a cube material. Okay, that is fine. All right, that is fine. So they say, at what angle to the normal does the ray leave the slab? Right. Let us reread this for the last time. Suppose light ray in air enters a cube of material this at that angle with respect to the normal and then exits the bottom of the cube into water. At what angle to the normal does the ray leave the slab? Now the first thing that we are going to do, I'm going to take my n1, which is 1.00, multiply that by the sine of the angle theta 1, which is 45.0 degrees, and then I'm going to equate this to n2, which is 2.50, and then I'm looking for the sine of that angle. Right, so let me just come here and see how this will work out. So I'm just going to say by Snell's law, 1.00 the sine of 45 divided by 2.50, and I am dividing there, divided by 2.50, and I get this. So I'm going to say sine the inverse of the square root of 2 over 5. So I'm going to say sine the inverse of the square root of 2 over 5. And what value do I find there? I find this as the angle of theta 2. So theta 2 is equals to 16.429. Right, let me just leave it as that. So let me explain what that is. Suppose light of this enters a cube. So when it is inside of a cube of material n equals 2.5, let's just come here, 2.5. If we can find it in here, it is not there. 2.5. Okay, that is fine. Okay, that is fine. Let's just leave it. So this is the angle, this angle that we have found in here. This is the angle that it makes when light enters inside of a cube. It will enter and bend away from the normal. And yes, I want us to notice something in here. You can see from here, let me show you something. The angle was 45, therefore light was traveling at a higher speed, and then the angle is 16. This light has slowly decreased the speed, therefore the wavelength as well, therefore the index of refraction is bigger. In here we can see that it was 2.5, and the angle of the index of refraction there is smaller, therefore n is 1. These are the fundamental things that we have learned. So it will enter inside of the cube and leave or bend away from the normal with that angle. But the question is, at what angle to the normal does the ray leave the slab? Right. So I'm going to take this, copy this, and now paste it there. Now I'm going to use the information of the cube because it is now leaving the cube now. So I know the index of refraction is 2.50 multiplied by the sine of the angle that I have just found, which is 16.429, and I'm going to equate this to the index of refraction. It is provided for me there into water, which is 1.333. so 1.333, the sine of this angle that I want to find. And then I'm going to just come here and I'm going to say 2.50, the sine of 16.429, and I'm going to divide that by 1.333. And what does that gives me? It gives me the angle theta. It gives me the angle sine theta. This is sine theta. Therefore, I'm looking for theta. So sine of theta is equals to 0.5304. Right. And then I know that theta, and then I'm going to say sine the inverse of 0.5304, and we should get the answer of 32 degrees there. And that's exactly what we find. 32.0 degrees. So these are the questions that requires one to think. They test whether we have understood the content, and then if we have understood the content, are we able to apply that we have understood in order to get that which is required. So this is what is happening. So now let us look what is happening again here. We can see when we compare from the cube to water, let's look at the angle. The angle here is 32, whereas the angle there was 16. So what does that tells us? It tells us because the angle is bigger in here, therefore light is traveling faster inside of water than it is traveling inside a cube of material n equals 2.50. Remember what we said. Because the index of refraction is bigger, therefore the wavelength is smaller, therefore light is traveling at a slower speed. The index of refraction is smaller, therefore we are expecting an angle there. So the angle here was an angle of let me just see. Oh, sorry, this is the air. The angle there was 16.429. So the angle here is bigger, telling us that light is traveling much faster and the wavelength is bigger. The angle there is smaller and the index of refraction is bigger, which was 2.5. So the bigger the index of refraction, the smaller the speed of light, and the smaller the angle. And the smaller the index of refraction, the bigger the wavelength and the faster the light is moving. Okay, we can continue in this. Now we are here, and then they are just trying to explain to us here. Now let us have this reading just to find out what is happening. Sorry. It's interesting to note that the speed of light in a vacuum is 3 times 10 exponent of 8 meters per second, is an upper limit of the speed of the material object. So this is the limiting speed. Nothing can travel faster than the speed of light in this context. In our treatment of relativity in chapter 26, we will find that this upper limit is consistent with experimental observations. So this was found via the experiment, so we cannot argue with that. And based on the conditions that they have set, this is that. Maybe somebody in some years to come will set up different materials for different environmental issues, and somebody might measure the speed of light in different ways, and we can protest on that. However, it's impossible for a particle moving in a medium to have a speed that exceeds the speed of light in that medium. However, it's possible for a particle moving in a medium to have a speed that exceeds the speed of light in that medium. So they say. Remember, and this was found via the experimental observations. For example, it's theoretically possible. It's theoretically possible for a particle to travel through a fused quartz at a speed greater than 2.06 times 10 exponent of 8 meters per second, but it must still have the speed that is less than the speed of light. That's fine. That is fine. Right, I thought, guys, before we can continue in any of these questions, let's just have something that might give us an idea as to how we should deal with all this. Let us just have something. Light infused quartz, very, very important. Right, let me just do this. So it is important that we come back here that the index of refraction equals the speed of light divided by the velocity, and that the index of refraction equals the wavelength of the light in a vacuum divided by the wavelength of light in a certain medium, and that frequency equals the speed of light divided by the wavelength, and velocity equals the speed of light divided by the index of refraction. Very, very important that we try to note that. Use the index of refraction to determine the effect of a medium on light speed and wavelength. Now, here is the problem. Light of wavelength 589 nanometer in a vacuum passes through a piece of fused quartz of index of refraction 1.458. Find the speed of light in a fused quartz. What is the wavelength of this light in fused quartz, and what is the frequency of light in this fused quartz? All right, let us try to do that. I know that the speed find the speed of light in a fused quartz. I know the speed of light, which is the velocity, is equals to the speed of light, which is 3 times 10 to the exponent of 8, divided by the index of refraction. Is the index of refraction provided here? Yes, the index of refraction in a fused quartz, it's 1.458. Can we also find that in here? Fused quartz, there it is, 1.458. So I'm just going to come here, and remember I'm looking for the speed, 1.458, and I find the speed of light inside of a fused quartz to be 2.05 to that, and this is less than the speed of light. And we have read that it is possible that light can travel inside of a fused quartz with the speed that is greater than the speed inside of that medium, but less than the speed of light. This is what we have read. It's possible for a particle moving in a medium to have a speed that exceeds the speed of light in that medium. So we have found a value in here, and this is the speed of light inside a fused quartz. So this speed might be the speed greater than the speed of light inside of that medium, but less than the speed of light. So this is the first question that we have answered. Find the speed. Secondly, what is the wavelength of this light in a fused quartz? And I know that frequency is equals to the speed of light divided by the wavelength. I cannot use this because I have two unknowns. And one thing that I know also is that they are asking for wavelength. One thing that I know is that I know that the wavelength, which is this, because this is the wavelength of light in a vacuum, I know that value there, it's provided for me as 500, and I think we looked into that. There it is, 589 nanometers alpha naught. So I know that one. So if I want to find the wavelength of light inside of that fused quartz, it will be this one, because this one is the wavelength of light in a vacuum. And what is this N? This will be the index of refraction inside of that fused quartz. Very, very important. So what is it that I'm going to do then? I'm just going to come here. Based on the formula, I'm looking for this. And what is this equals to? It's equals to that divided by this. Very, very important. So I'm going to say 589 nanometer times 10 minus 9 and I'm going to divide that by the index of refraction inside of that fused quartz, which I have found to be 1.458, and I will get the wavelength as that. Right, can I try to write this in a different way? Let's just write this as normal. So I will press just 1 and I find this to be that, and I can just take maybe 2 to the side and this will give me that in nanometers. So that's exactly what I will get. So that would be, for example, 404 nanometers. If I move these to the side, and then I will have -8 -9. So that would be this. You can just leave it in this way. That is also not a penalty on that. So this is the wavelength of light when it travels inside of this medium, which we call a fused quartz. And then lastly, I think was for us to find the frequency of light in this fused quartz. So frequency equals the speed of light divided by the wavelength. So I know what the speed of light is. That's 3 to the exponent of 8. And I can divide that by the wavelength that I have just found. And what will be the wavelength then? The wavelength is the wavelength in here, the wavelength inside this fused quartz that we have just calculated, or is this wavelength the wavelength of light moving in this speed? Which one are we going to use? Which one are we going to use? It is very, very important that we ask ourselves this question. When they say, let me just place that. When they say, what is the frequency of the light in a fused quartz? What is the frequency of that light? So when we say that frequency is equals to the speed of light divided by the wavelength, it has to refer to the wavelength of this speed of light. It cannot refer to this wavelength, because look at the speed that we are using there. We are not using the speed of light that we found as 2 point something. No, we are not using that speed here. So because we are using the speed of light in a vacuum, we need to use the frequency, the wavelength of light in a vacuum, which is this value. So that's exactly what we are going to do. It's very important that we note that. So I'm going to use 589 to the exponent of -9. And I will find that frequency as 5.09 exponent of 14 hertz. So that would be that. And then I will leave this for you to try and work on.